Probability is a measure of chance or likelihood, and the probability of an event happening tells us how likely or unlikely it is to happen. When we talk about an event, we just mean a thing that happens. Tossing a coin, rolling a die, the weather being wet, or something like a red car passing us by. Now, this is actually something we do all the time. We do talk about chance and likelihood in life generally. And we do it on a kind of scale. And at one end of the scale, we have events that are impossible. There are certain things that will never happen. And at the other end of the scale, we have events that are certain, guaranteed to happen. And any event that we want to think about, any event that we could consider, will either be impossible or certain or somewhere in between. In particular, we have events that have an even chance of happening. They are equally likely to happen or not happen. Now, having these three markers on this scale, impossible, certain, and even chance in the middle, we can also consider a couple of other descriptors. We can consider this area here, somewhere between impossible and equally likely of happening or not happening. And anything falling into that kind of gap must be unlikely. We can also think about, similarly, this gap here, a greater than even chance of happening, but somewhere less than certain, and those events must be considered to be likely. Now, we could apply one of these 5 words to any event that we want to think about, as long as we had enough information or knowledge about that event. For example, the probability of Sunday following Saturday. Well, I would say, as far as we are aware at least, that is pretty much guaranteed to happen. Sunday will always follow Saturday, so we could probably mark that on our scale as certain. Another event, the probability of tossing a coin and getting a head. Well, realistically, there are 2 options for a coin toss. We get a head or we get a tail. There is the very, very slim chance that the coin could land on its side, but because that is so slim, we can pretty much ignore it as a chance, and we can talk about head or tail, 2 possible outcomes, each one equally likely to happen, so there is an even chance of tossing a coin and having it land on a head. We could look at slightly more vague events. We could look at something like the probability of there being a red car in a car park. Now, yes, granted, it does depend on the particular car park, maybe the time of day, maybe where you are in the country. There are factors that influence this, but we could probably say, because we know that red is a fairly common colour of car, we could probably say that that is likely. Different people might give slightly different answers there. If you have a red car and you know your red car is in the car park you're looking at, you could say it was certain, but we could probably say it was definitely at least likely. We could talk about something like the probability of rolling a die and getting a 2. Well, weird as this may seem, this is actually unlikely. There are 6 options on a standard fair 6-sided die. 5 of those options are not a 2. So it's actually more likely that we get an outcome that isn't a 2 than an outcome that is, meaning it is, on balance, unlikely that we would get a 2. Now, the problem with these words, particularly for those last 2, the car and the die, is that they are a little bit vague. One person's likely might be another person's unlikely. And even if we accept what the words mean, where on the scale are we putting them? Is something likely as in almost certain, but not quite? Or is something likely as in there is just a slightly greater chance of it happening than not happening? It's just a little bit above even. And how would we know? How could we prove that? If we were looking at 2 events and we labelled them both as likely, how would we be able to say one is more likely than the other? What evidence might we need to collect? How might we be able to compare them? And that's the problem with these words. They're not very easily comparable. But it would be helpful if we could have a way of comparing probabilities so that we could talk about one event being more likely or less likely than another event. And to do that, we turn to numbers. We come up with a way, that we will talk about shortly, of assigning a numerical value to any chance that we are interested in. And by assigning those numerical values, we can then make comparisons and we can put them somewhere on this scale. And we start to do this by thinking about the following three options. We just focus on our impossible, our certain, our even chance in the middle. And we say that the numerical value that we're going to assign to impossible is 0. There is a 0 chance of that event happening. Now we need to give certain a value as well. And we choose the value for certain very carefully so that our list does not become impossibly large numerically. When we give certain the value 1, we say that there is a 1 chance of it happening. The numerical value we assign is 1. Now that means that we're then forced to pick a certain value for even chance. Even chance falls nicely in the middle. So we want the number that is exactly halfway between 0 and 1. Well, yes, we could give that as 0.5. In fact, we're going to give that as a half. Probabilities are generally given as fractions. It is entirely possible to give probabilities as decimals or even as percentages because they all three mean the same thing. They're just different ways of writing them. But we tend to stick with the fraction for reasons that will become clear very shortly when we look at how we're going to find them. But this is our basics of finding numerical probabilities. 0 for impossible, 1 for certain, and half for an even chance. So the only thing we need to do now is we need to think about how we're going to find those numerical probabilities.
So now we've got this idea that probabilities can be assigned a number, chance can be assigned a number between 0 and 1. We need to have a way of actually working out the numerical probability, the numerical chance for any event so that we can assign a number to an event and then we can work out where on our scale it must go. And we can compare chances for different events. So think about what we've already seen, and that's the probability of tossing a coin and getting a head. Tossing a coin and the coin landing on a head. And we said that was 1/2. We said it was an even chance. We didn't assign a numerical probability to it at the time, but we said it was an even chance. And we now know that even chance is 1/2. Let's focus in on this number a little bit more, because this is our kind of springboard to how we're going to work these probabilities out. Ignoring the option of the coin landing on its side, because that is a negligible chance, there are 2 possible outcomes for tossing the coin. The coin is either going to land on head or it is going to land on tail. There are 2 possible options. Those 2 options are head and tail. Only one of the 2 possible options is head that we are interested in. Only one of the options is what we are interested in. 2 options in total, 2 possible outcomes, one of them being what we are interested in, what we're looking at. And that is how we're going to work out probabilities, any numerical probability. So, to find the probability of an event, we set up a fraction. And on the bottom of the fraction, we have the total number of things that could happen. On the coin toss, we could either get heads or tails. That's 2 things that could happen, so 2 went on the bottom of the fraction. On the top of the fraction, we have what we are interested in. So the number of times the event happens, or can happen. There is 1 head on a coin, so we could have a 1 on the top of that fraction. So the probability of an event equals the number of times the event can happen, the event that we're interested in, on the top of a fraction, and then on the bottom of a fraction, the total number of things that could happen. quick mention of some notation before we work a few of these out. This is very much an optional thing. Do you have to use this notation? No, you don't. I am going to use this notation because it is quicker to write. Because it can be quite slow to keep writing the probability of, and then have to actually write down the event itself, we can shorten that and we can use brackets with a P on the outside. So P and then something in brackets means the probability of. For example, probability of, if we were tossing a coin and getting it to land on a head, we could just write the probability of a head. And it is implied there that we mean a head from tossing a coin. Probability of a red car in a car park, we could have probability of red car with the red car in brackets and the P on the outside. Do you have to use this notation? No, you don't, but I am going to make it easier to write down what I'm doing. So key takeaway, we can work out the probability of any event by writing a fraction, and we're always going to leave our probabilities, or we're generally going to leave our probabilities as fractions. Okay, so let's consider some actual events. Well, classic options that we might have to deal with: toss a coin. Probability of a head, we've already seen, is 1/2. Even chance, but let's just check that with this definition we've got. So on the bottom of the fraction, the total number of possible outcomes. Well, for a coin toss, it will either be head or tail. So there are 2 possible outcomes. On the top, how many of those are what we're interested in? How many of those options are a head? Well, just 1, so 1/2. Similarly, probability of a tail from a coin toss. 2 options in total, head or tail. 1 of those is a tail, so 1/2 as well. Hence the even chance, equally likely to be a head or a tail. Other classic thing to think about, one of these. A standard fair 6-sided die. 1 die, 2 or more dice. If we roll a die, there are a number of different options we could consider for probabilities. We could, for example, think about the probability of rolling a 1. Well, how many options are there in total? Well, we've got to get a 1, a 2, a 3, a 4, a 5 or a 6. So there are 6 different options for possible outcomes. How many of those are a 1? Well, 1 of them. There's only one 1 on that die. Every other side has a different number on it. It's just the one side that has a 1. We could think about other stuff as well. We could think about the probability of rolling an even number. Well, there are still 6 options. How many of them are even? Well, 2, 4 and 6. So that's 3 even options. You might notice that 3/6 will cancel down to a half. Usually we would do that. In this case, I'm not going to. I'm going to leave it as 3/6, just because it's then easier to see where these numbers have come from. We can see that it's 3/6 because there are 6 options in total for possible outcomes, 3 of them being what we're interested in. We could get the probability of not a 4. For example, 6 options in total. How many of those are what we're interested in? How many of those are not a 4? Well, 1, 2, 3, 5 and 6. So that's 5 options. And there is a 5 out of 6 or 5/6 chance of rolling not a 4 from a standard fair 6-sided die. Consider this bag of counters. In the bag of counters, we have got red counters, green counters, and blue counters. If we wanted, for example, to work out the probability of dipping our hand into the bag and picking out a red counter, we would need to know 2 pieces of information to set up our fraction. We would need to know on the bottom how many possible outcomes there are in total. Well, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 counters in the bag in total. So there are 12 possible outcomes. On the top, we want the number of those outcomes that are what we're interested in, that are red counters. So there are 1, 2, 3, 4 red counters in total, giving us a probability of 4 out of 12. Probability of blue counters, say, 1, 2, 3, 4, 5 counters out of the 12 possible options. probability of green counters. 1, 2, 3 out of the 12, giving us probability of 3 out of 12. There are other probabilities we could look at here as well, slightly more complicated ones. Probability of red or green, say. If we wanted the probability of red or green, well, on the bottom of our fraction we'd have how many possible outcomes there are, and that's still 12. But on the top we'd need how many of them are red or green. Well, that's 1, 2, 3, 4, 5, 6, 7 are red or green. 4 reds and 3 greens gives us 7 counters in total and a chance of 7 out of 12. We could even have something like this, probability of yellow. Well, there are 12 possible options. How many of those are yellow? None. So we can have 0 out of 12. But hopefully we'd think a little bit more than that, and we'd think, oh, well, surely just 0 out of 12 is 0. There is a 0 chance of pulling out a yellow. It is impossible. Thinking about the bag of counters that we've just seen, we had the probability of pulling a red counter out of the bag was 4 out of 12. The probability of pulling a blue counter out of the bag was 5 out of 12. And the probability of pulling a green counter out of the bag was 3 out of 12. Something interesting happens when we look at these 3 options together. Notice first of all that they are the only 3 options. We will either get a red counter, or a blue counter, or a green counter. We're never going to get anything else, and they are in fact all of the options. I'm going to do something with them. I'm going to add them together. I'm going to add the probabilities of those 3 options together. I'm going to do 4 over 12 plus 5 over 12 plus 3 over 12. When we add fractions, remember, the number on the bottom, as long as they're all the same number, stays as it is. So we're going to have a 12 on the bottom. 4 and 5 and 3, we add the top numbers together now because they're all the same type of fraction. 4 and 5 is 9, plus the 3 is 12, and we've got 12 out of 12. And hopefully common sense will prevail, and we notice that 12 out of 12 is simply another way of writing 1. Now, why does that make sense? Well, think about it. 1 is the probability for when something is certain. And we are guaranteed to either get a red or blue or green counter when we reach our hand in and pull a counter out. The counter isn't going to magically disappear. We're not going to put our hand in and pull something else out. We're not going to put our hand in and pull a yellow counter out, or anything other than a red, a blue, or a green. We are guaranteed to have one of those options. Therefore, if we add together the probabilities for all of the options, we get 1. Does this work in other cases? Let's have a think about the die again. If we think about a standard 6-sided die, we could either get a 1, a 2, a 3, a 4, a 5, or a 6. They are the possible options. And the chance for each of those, if we added them together, will cover all of the outcomes. Well, what's the chance of getting a 1 on a standard 6-sided die? It's 1 out of 6, because there's 6 options in total. One of them is a 1. Probability for 2, 6 options in total. One of them is a 2. Probability for 3, 6 options in total. One of them is a 3. And the same for 4 and 5 and 6. 1, 2, 3, 4, 5, 6. 6 sixths or 1. And the same has happened again. Summing the probabilities, adding up the probabilities for all the different options so that all of the options are covered, no overlap, no options missing, gives us 1. We can even think of a really simple one with the tossing a coin. Tossing a coin, we're either going to get a head or we're going to get a tail. If we think about the probabilities for those two and sum them, half for a head, half for a tail, 2 halves, or 1. And once again, the probabilities for all the different options sum to 1. If we consider all the possibilities, the probabilities will add to 1. Final note on probabilities, we are using fractions for our probabilities. We know from previously that fractions can be written in different forms that are still equivalent. We can have equivalent fractions. We can also rewrite fractions as decimals and as percentages. It is perfectly acceptable to give a probability as a decimal or as a percentage. We will very occasionally see probabilities given as decimals. Generally, though, we're going to stick with the fraction form. But it is okay to use decimals and it is okay to use percentages. We're just generally going to stick with the fractions. If I toss a coin, then the probability of getting a head is 1/2. That means for every 2 throws, I'm expecting one of them to be a head. Does that mean that I will get exactly 1 head out of every 2 tosses of a coin? Well, no, it doesn't, because it's what I'm expecting. And 2 throws, that's not enough to make a really particularly good judgment. But with a 1 in 2 chance, if I toss a coin 500 times, how many heads would I expect? Well, the key word there is this word, expect. We cannot accurately state exactly how many heads we would get from 500 tosses of a coin, standard, fair, even coin, unless we actually did 500 tosses of the coin. But by thinking about how many heads we would expect, I can reach a number. If I expect 1 out of every 2 tosses of a coin to give me a head, then I would surely expect half of the 500 coin tosses to give me a head. So I would expect 250 heads from 500 tosses of the coin. Does that mean that we get exactly 250 heads from 500 coin tosses every single time we did 500 coin tosses? Well, no, of course it doesn't. Keyword, again, is expect. The point is, if we get 248 heads or 256 heads, that's probably fine. That's okay. If we came out at something like 30 heads from 500 coin tosses, we might start to question whether there was something perhaps wrong with the coin, whether it perhaps was a weighted coin or wasn't fair. We might start to wonder whether there was perhaps some sort of bias to it, i.e. being not fair. And this idea of fair, we can firm this up a little bit. This idea of fair means that there are equally likely chances. As in for similar events. A fair coin, equally likely for all the possible options. A fair die, equally likely for all the possible options 1, 2, 3, 4, 5 and 6. A biased coin would favour heads or tails, so we'd expect more heads or more tails. A greater chance of landing on head or a greater chance of landing on tails. A biased die would favour one or more of the numbers, so a greater chance of landing on that particular number. This idea of expected outcomes or expected values is something that we can work with then. This idea that we can use the fraction and we can use a total number to give us an expected value of outcomes. If, for example, I were to roll a die 600 times, how many 4s would I expect? What is the expected value for the number 4? Well, the probability of a 4 on a standard 6-sided die is 1 out of 6. So I would expect 1/6 of the 600 times for rolling the die to be a 4. I would expect 1/6 of 600 would be 100 4s. Doesn't mean I'm going to get exactly 100 4s. I might get slightly more, I might get slightly less. But if I get something that's massively different from 100, then I might start to wonder whether my die is biased in some way. Consider a spinner numbered 1 through 5. The spinner is fair. Now, if the spinner is fair, that means there is an equally likely chance of landing on any of the outcomes, which means the probability of 1, and the probability of 2, and the probability of 3, and the probability of 4, and the probability of 5 are all the same. They are all going to be, there are 5 options in total, and one of them is each of those numbers. So 1/5 for each of them, if the spinner is fair. But imagine if now I nobble the spinner in some way. I make it so that the spinner is not fair. For example, I might put a weight under, say, the number 2. There is now a greater chance that the spinner will land on the number 2 and a lesser chance that it will land on any of the others. If the probability of the spinner landing on 2, now that we've weighted it, is now 1/3, and the other options are all equally likely, what is the probability of the spinner landing on 4? Well, the key thing here is that the other options are all equally likely as each other. We know what the probability of 2 is, and we know that the other 4 options are equally likely. So how are we going to work through this question? Well, the key thing is we know something about the different options. We know something about probability of 1, and the probability of 2, and the probability of 3, and the probability of 4, and the probability of 5. Well, whether they're the same or different, they are all the possible options, 1 or 2 or 3 or 4 or 5. So those 5 probabilities must all do something. They must all add up to 1. Now, if they all add up to 1, and we know what one of them is, then to work out the other 4, we could do 1 take away the probability of 2, i.e. 1 take away that third, leaving us with 2/3. That means that 1/3 of the chance is contained in the 2. 2/3 then must be equally shared among the other 4 options, i.e. probability of 4 is going to be 2/3 divided by the 4. They're all going to be the same. We could put that in a calculator, 2/3 divided by 4, sharing the remaining probability from the total of 1 out among the 4 options, 2/3 into a calculator divided by 4, 1/6. And the probability of 4 must be 1/6. And it all hinges on this idea that all of the probabilities for all the possible options will add to make 1.